Welcome to the presentation about pipeline compression in remote GPU virtualization systems using rCUDA, early experiences. My name is Christian and this is work that I did in support of my PhD under my advisors Carlos Reaño and Federico Silla at Universitat Politécnica de Valencia from Spain. This work is a contribution to the second international workshop on deployment and use of accelerators. Let us begin with a motivating example such as a typical IoT environment. In these environments, several data must be analyzed, such as the temperature, the current weather, or even some images. These data are usually obtained by IoT devices. The advantages of these devices are principally their low energy consumption and their low cost, while the most important disadvantages are they have low performance and are usually located in environments with slow bandwidth networks, such as Wi-Fi or cell phone networks. Due to the low performance of the IoT devices, data obtained is usually sent to the cloud to be analyzed in a cluster or a high-performance device. Note that the network use typically have slow bandwidth, as I commented before. Edge computing has been a good improvement, because this approach alleviates the network problem by processing all or part of the data at the edge of the network, that is, on the IoT device, commonly called edge device. Edge devices may not be able to support any type of applications. For instance, machine learning applications are normally developed using PyTorch or TensorFlow frameworks. These frameworks are currently boosted by using GPUs and the CUDA programming technology created by NVIDIA. These devices don't usually have GPUs, so they cannot be boosted by them. A possible solution would be to use remote GPU virtualization. In this way, an application can access a GPU located on a remote computer. Remote GPU virtualization approach has demonstrated to be a significant advance for edge computing. The most important remote GPU virtualization systems are rCUDA and gVirtus. Although both solutions follow the same architecture, we use rCUDA in this work, because rCUDA supports more functions than gVirtus. How does remote GPU virtualization work? Well, these solutions typically follow a client-server architecture. On the client side, a library intercepts all CUDA functions, while a daemon runs all the functions intercepted in the CUDA library on the server side. Then, for each call to CUDA functions in the application, the client library intercepts the GPU request, processes the request information, and sends it to the server side over the network. On the server side, the daemon receives the GPU request and sends it to the GPU. The GPU returns the result to the daemon once the request has finished. Then the daemon sends back to the client side the result of the request. And finally, the GPU accelerated application interprets that result. The remote GPU virtualization approach works transparently to the application, so the application doesn't know if the GPU request is served remotely instead of locally. Also, the source code doesn't need to be modified to use remote GPU virtualization solutions. As I commented before, the network used by edge devices usually has low bandwidth, and it can be a problem in these solutions. For that reason, we have proposed in this work a compression system in the communication layer of the remote GPU virtualization to artificially increase the bandwidth obtained. Note that, as the remote GPU virtualization approach, the compression system works transparently to the application. Implementing an on-the-fly data compression within a remote GPU virtualization middleware must be done in such a way that the overhead of the compression and the compression task don't cancel the benefits of transmitting a smaller amount of data. A naive implementation of on-the-fly data compression is the following. As soon as the application performs a call to a CUDA data copy function, the client middleware intercepts the data to be copied, compresses it, and sends the compressed data to the server side. Once the compressed data is received in the server side, The Remote GPU Virtualization middleware decompresses the data before forwarding it to the GPU. In the opposite direction, a similar process is followed. First, the GPU data is transferred to a host memory. Then, is compressed and sent to the client side. Once the compressed data is received in the client side, the Remote GPU Virtualization middleware decompresses the data in the final location. This naive implementation can be largely improved by a pipeline approach. In this case, the implementation of on-the-fly data compression is as follows. As soon as the application requests a CUDA memory copy, the client middleware intercepts the data to be copied and splits it into several data chunks. Then, the client middleware compresses the first chunk. Once it is compressed, it begins compressing the second chunk. At the same time that the second chunk is being compressed, the client middleware sends the first compressed chunk to the server. This process continues with the rest of the chunks. By doing this, compression and network transfers overlap in the client side of the middleware. On the server side, a similar approach is followed, and the network transfers, the compression, and copies to the GPU memory overlap. Once the compressed chunk is received, the server decompresses the chunk, and after that, the chunk is copied to the GPU. At the same time that the first chunk is being transferred to the GPU, the second chunk is being decompressed, and the third chunk is being received. In both sides of the middleware, the client and server one, overlapping compression stages with data transfers hides the overhead of compressing and decompressing data. In the opposite direction, a similar process is followed. Note that the pipeline is obtained when these gaps work with different data chunks at the same time. In this work, we have evaluated 4 different machine learning applications to evaluate our compression proposal in the context of remote GPU virtualization solutions. LXNet application, where the inference time of LXNet convolutional neural network model is evaluated. CIFAR10 application. This application uses CIFAR10 dataset to evaluate the image classification of a simple convolutional neural network. MNIST application. Using LeNet-5-like convolutional neural network model, the application evaluates the image classification of MNIST dataset. And Inception application. This application uses Inception convolutional neural network model to classify a flowers dataset created by TensorFlow. We have been focused on the end-to-end open source platform for machine learning applications called TensorFlow. It has been developed by Google and allows users to easily build and train machine learning models. These applications have been extracted from TensorFlow tutorials. There are a large number of compression libraries where each one is based on different compression algorithms or is focused on working with different types of data. To choose the compression libraries in this work, we have used SMASH. SMASH is a compression benchmark created by us that contains 41 different lossless compression libraries. These compression libraries compress data located in RAM. Also, SMASH allows users to test those compression libraries and configure their options. Compression libraries usually have different options which directly affect the compression ratio, compression speed, and the compression speed. Using the SMASH benchmark, we have selected 6 different compression libraries that show representative and interesting results: LSET4, setlib, setstd, snappy, gibfeli, and fastlset. All of them has been based on LSET77 algorithm. Each library follows different strategies to obtain better computation time or compression ratio than others. In the experiments, we have used a Raspberry Pi 4 Model B as edge device. In the case of the remote GPU server, it has an NVIDIA V100 GPU. The focus of this work is on edge devices featuring low performance networks, so we have limited the bandwidth of the network to 10 megabits per second. For that purpose, we have used the Linux traffic shaper called TC.
To evaluate the benefits of our proposal, we have considered the following scenarios. In first place, we have run the applications using only the CPU of the edge device. Then, we have run the applications of loading computations from the edge device to the remote GPU server using rCUDA over the 10 megabits per second network. In this case, we have done experiments without compressing the data transferred between the edge device and the remote GPU server, and compressing data transfers with the compression libraries under analysis. We can observe that using rCUDA without compressing data transfers increases execution time between 1.4 and 25 times more than when using only the edge device CPU. These results clearly show that optimizing data transfers is essential for achieving better performance with rCUDA. One such optimization is the on-the-fly data compression proposed in this work. Using rCUDA and data compression improves the results in all the cases when compared to using rCUDA without compression. If we compare the results to the ones of using only the edge device CPU, we observe that only the MNIST application performs better with rCUDA with compression. To research on the reasons for these results, we analyze a histogram of data transfers when the TensorFlow applications under study are run. The y-axis represents the percentage of data transfers done in a specific range of sizes, while the x-axis represents the size of the data transfer. For instance, the range labeled as 8 bytes and 16 bytes includes all the data transfers carried out during the execution of the TensorFlow applications, with sizes ranged between 8 bytes and 15 bytes, including both. As we can see, data classified in this size range represents more than 35% of all the data transfers done by all the TensorFlow applications. Moreover, as it can also be observed in the histogram, more than 90% of the data transfers have a size between 1 byte and 1023 bytes. The pipeline in rCUDA was implemented with chunks of 1024 bytes, and we add the compression in this pipeline. That could explain the results obtained in the previous figure, where the compression reduced the execution time between 1 and 6 minutes. So, we can ensure that compression libraries aren't taking advantage of rCUDA compression pipeline, because most of the data transfer is smaller in size than the chunk used to split the data. We are using the naive implementation of on-the-fly data compression. In addition, it should be noted that compression libraries usually perform better with larger data, because the more data, the more information is repeated. We have analyzed the size of data transfers in the range of 8 bytes and 16 bytes, which represents more than 35% of all the data transfers done by the TensorFlow applications. This table shows the number of data transfers done by each TensorFlow application in that range, and the number of the different data values used in these transfers. We have discovered that all the data transfers have a size of 8 bytes within that range. So, data can have up to 2 to the 64th power of different values. However, despite the large number of data transfers, TensorFlow applications seems to use less than 2 to the 16th power of different data values. So, data could therefore be represented by 2 bytes instead of 8 bytes. Okay, here we have seen there are between 3,000 and 25,000 different data values that depend on the TensorFlow application. Let's see what happens with the most repetitive data. This figure shows the percentage of data transfers of the most repeated 8-byte data values when running the TensorFlow applications under study. Due to the large number of the different data values, we have discarded values with a percentage of the data transfers below 0.2. The most repeated 8-byte data are different for each TensorFlow application, but the aggregate percentage of data transfers for this data represents between 43 and 68% of all the 8-byte data transfers. As we can see, there are around 20 different values per application, so we will need only 1 byte instead of the 2 bytes obtained in the previous optimization, because there are less than 256 data values. Considering that these data values represent a high percentage of all the transfers, these optimizations will considerably reduce the size of the data sent over the slope network. Note that 43 and 68% of all the data between 8 and 16 bytes can be represented with 1 byte, while the rest of that range with 2 bytes. In this table, we can compare the raw size that represents all the data transfers between 8 and 16 bytes, uncompressed, and the size obtained with the optimizations proposed. LXNet application will reduce almost 100 kilobytes in its transfers. CFR10 application around 200 kilobytes. MNIST application more than 500 kilobytes, and Inception applications more than 600 kilobytes. In this work, we have focused on addressing the slow network problem when edge devices use Remote GPU Virtualization Systems. An initial pipeline implementation of on-the-fly data compression has been developed to improve network bandwidth. We have used 4 popular machine learning applications to evaluate our proposal. The on-the-fly data compression proposed is able to reduce between 1 and 6 minutes the execution time. However, performance still needs to be further improved. Analyzing data size used by applications, we have realized the importance of small data, where more than 90% of the data transfers have a size lower than 1023 bytes. We have pointed out different ways to improve the performance of our pipeline on the fly data compression mechanism, focusing on 8-byte data, where some applications will reduce their data transfers up to 600 kilobytes. I would like to finish the presentation by thanking you for attending this talk. Also, I would like to thank my advisors for their support in this work. If you have any questions, feel free to contact me.